So I built a half bridge inverter. And to prove that it worked, I said that I'd play music, turning this into a D-class amplifier. The premise was simple. We take audio samples from the SD card, use our STM32 to convert it to PWM, sends it to the half bridge. The half bridge converts it to music. Sounds simple, but it isn't. We used the wrong filters, which robbed power from the speaker, and then we found out that two tiny capacitors were responsible for creating a high-pass filter, which didn't make the speaker work. Then after replacing them with bigger capacitors, we then brought the amplifier to life. But then we had another problem. We had nasty transients. You know, of a 12-volt switching node, we got 25 volts and then negative 9 volts. So in this video, I'm going to show you the major mistakes I made, hopefully save you a lot of time if you're trying this for yourself. And it's going to be a good video, so stay tuned to the end. Look at this monstrosity. But, you know, for 200 kilohertz, that's a pretty, it's got a little bit of noise, but I guess I'm assuming the noise is coming from my flying wire I did back here, if you can see it. All right, what you saw there was the output with an RC filter, a resistor capacitor. Now, this is why you should never do a resistor capacitor on a D-class amplifier, is because the resistor will literally rob voltage from the load, from the speaker in this case. The speaker is 4 ohm, okay? So even if you have a small 100 ohm resistor in your filter, you have that voltage divide now. So the 100 ohm is gonna rob most of the voltage from that 4 ohm. If you do the math, it's crazy. You end up getting literally no voltage at the speaker, and it sounded just crap. I couldn't hear nothing, and it wasn't even worth showing you guys. So what I've done is I've added an LC, a inductor capacitor filter, which doesn't steal any voltage and is what's used in actual D-class amplifiers. Now, I still have a problem, and let me show it to you. As I know it looks like a mess, but we have the speaker here, we have the SD card here, STM here, half bridge here, and then we've got power, and we're probing it to measure it on the oscilloscope. And now I'm going to put this orange clip, and you're going to hear how it sounds. So that's the problem we're currently facing, which it's actually fixable, I think. It's not the worst problem to have. It could be a number of things. What I'm going to try is I'm going to try to reduce the amplitude of the actual samples. So when I exported it from Audacity, it was 0.8. So I'm going to reduce it to 0.5, and then we're going to see if that fixes anything. I doubt it. I'm assuming it's clipping maybe, but it doesn't look like it's clipping on the oscilloscope. But that's just the next move. So we'll see what happens. So this is the sound it's making when I put 500 hertz and the amplitude to half. It still sounds terrible. But I've probed both sides of the speaker and they're exactly identical. Okay, so this is an interesting view, right? The blue is after the filter, so that's obviously the sine wave, and the yellow is the carrier wave. Now you can see that the blue isn't going to the top or the bottom of the carrier wave, and that's because we've clipped it at 50%. So it's going like 25 up and down, 25% up and down, right? Because if I zoom out, then you can see it's a really good example of, see that? Unreal, hey? And you can see that carrier wave. That's probably the best example of how a carrier wave works. And you can see it exists only 50%. Now I've done this to hopefully remove this ugly clipping or whatever I'm hearing here, but it must be a deeper problem. That 0 volts across the speaker is confusing me. So I've hooked it up to here to see if I've got the right signals. And they're, you know, complementary to each other. They're perfectly complementary. The only thing is maybe it's the dead time. Look, there's quite a bit of dead time. Now if we have a look at the time, what do we have for the dead time here? It's roughly about, we've got about 500 nanoseconds of dead time. Could that be the problem? I don't know. I don't think so. Like, come on, really? Could that be the problem? So we keep debugging. This is actually really cooked. Now the speaker's dead. I had it playing, I was trying to probe, and then I hear like a big zzz, and then nothing. The board's still on. This doesn't work anymore. And it's like, what the far out? It shouldn't be this hard, right? Shouldn't be this hard, but yeah, problems. Hey guys, I took all the filter off and I just put like a resistor back on, like a really big one. And you know it's cooked when you get just a solid line, and this is the other side of the resistor. Yep, nothing's working. So I'm going to assume that this is going to be the gate driver, and then we're going to have to solder it back on. We'll take it off and solder a new one on and see if that fixes it, because maybe they're just so sensitive. I don't know what the hell happened. I really don't know. I think the alligator clip shorted something on the board. That's my best guess, but anyway, we'll do that and come back and see what happens. So after rebuilding the circuit, here's the new one that I rebuilt. We're back at square one. We're right back where we started. And I'm just not sure why the speaker wouldn't be playing. So we're gonna have to work that out before we blow this up again. Oh my gosh. I am so happy, right? I've just figured out the problem. And it took a long time, but I finally figured it out. It's the capacitor bank. If you don't know what I'm talking about, I'll put it up on the screen now. The capacitor bank was filtering out my low frequency audible range. Now it makes sense because when I put like I think I put a 47,000 ohm resistor over the load, and I just ran it with the PWM without the low pass filter, and it worked, right? Because these capacitors allow high frequency to pass. So what was happening is that high frequency was able to return to ground right through the capacitors. Because at high frequency, the capacitors are going to provide like, not a short, but they're passing current. Now low frequencies, they don't do that. So what was my audible frequency range? It was low frequency. It was like under 20 kilohertz. It was, to be exact, 1,000 hertz, right? My carrier wave, when I put the load on, was 200 kilohertz. So that was able to pass through nice. And I was getting a voltage difference over the load. When I put the speaker on, however, nothing. I was getting not even a voltage drop across the speaker. These capacitors are to blame. They're filtering out my low frequency. They're not allowing it to go to ground. So here's what I've done. I've just ordered these bofers. Look at these things. They're huge. I don't even know if they're going to fit, but it's going to be a monstrosity, but it's going to work. These are 4,700 microfarad capacitors. These are supposed to allow my low frequency audible range to pass through to ground, okay? So what I'm gonna do is I'm gonna take these off, I'm gonna solder these on, and we're gonna run it again, and hopefully, just hopefully, we're gonna get some music. Man, if this works, I'm gonna be so happy. Okay, I got it wired up. That's what it looks like. Complete abomination, but we should hear a difference. So I'm gonna wire this up now. I'm gonna connect it all. I'm gonna turn the power supply on at about 11.7 volts. Okay, you ready? What the hell is happening? Ah, shit. It broke. Ah, they're so thin. This thing broke right here. Let me show you. This yellow... This yellow cord broke off from this white one. That should be together and it broke off. So solder it and come back. Got me worried there. All right, it's fixed. Let's try again. Oh. Okay, I got it working again. It was, oh my gosh, this is really frustrating. I had it on the wrong pin. All right, let's try again. Oh, we got a solid. All right. A bit noisy, but I can definitely hear that sine wave. That's noisy though. Wow. It's so much louder than before. 1000% louder. And we're actually pulling 100 milliamps. So we're actually pulling current, but something is still wrong. Something is still wrong, so we're going to put it on the oscilloscope to have a look. It's progress. There's definitely a lot of transient noise. Oh, look at that. Oh, look at that. That is what I want to see. If I do the math on that, oh, perfect. Oh, that is perfect. Good stuff. All right, but we are getting some nasty transients. See these spikes here? I'm worried that's what's making the speaker sound really, really bad. See these here? So we're gonna have to fix that up. Okay, so the result is that, I'm gonna put the photos up here, but those transients were really, really bad. Like we're getting off, the square wave is going 0 to 12 volts and we're getting it hitting 25 volts and then shooting down to like negative 9.3 volts, which is terrible, terrible. Having a negative 9.3 volts actually makes the gate voltage of the high MOSFET a lot higher. So not very good. So this is going to require a board redesign, which means that we're going to have to end the video right here. But I promise you that we will get this working. It's just a lot harder than I anticipated, and it's not simple at all. When we go into really high frequencies, just board layout matters so much, and clearly it's screwing me over. Now, there could be some issue with the software, but when I saw that extreme overshoot and that really noisy transients, I want to address that issue first before we address any software issues, because that is a really bad one, and it's because of board layout. And we've thrown these capacitors on here, we've put an external LC filter on here. It can create extra noise, but also layout, trace length. There's no snubbers, and there's nothing like that. We can add extra capacitors. There's ways that we can reduce that ringing, and that's what I want to do first. I want a waveform that looks really clean, and it did look clean actually. When we tested it, it really did look clean for a load that drew very little current. But when we put a speaker on here that's demanding really high current, like hundreds of times more current than that resistor did, then it exposes all our faults and flaws. So this, what I've done is, I'm not going to leave you with nothing. I've put Interstellar, a short snippet of Interstellar on this speaker, right? And I'm just going to show you how it sounds, because it sounds really bad. So you listen to it fluctuate. Really bad. Really terrible. So yeah. So I guess I'll see you in the next one, and take care.